Welcome! In this session, we'll explore problem number 528, random pick with weight. This problem challenges us to design a solution that efficiently picks an index based on weighted probabilities. We'll discuss the intuition, approaches, and complexities step by step. Let's dive in. This problem requires us to design a solution where we can randomly pick an index from an array, but the probability of picking that index is directly proportional to its associated weight in the array. To achieve this, we are provided with an array of positive integers, w, where each element w, I, represents the weight of the ith index. We need to implement two key components. First, we must initialize the object with the weight array w. Second, we need to create a method called pickIndex that will randomly return an index, ensuring that the likelihood of selecting any given index corresponds to its weight divided by the total weight of the array. For example, if an index has twice the weight of another, it should be twice as likely to be selected. The input consists of the weight array during initialization, and the pickIndex method, which returns an integer. While the initialization step doesn't produce any output, the pickIndex method will return the randomly chosen index based on the defined probabilities. To better understand the problem, consider the first example where the weight array is w equals 1, 3. Here, we initialize the object with this array and then call the pickIndex method multiple times. In this case, the total weight is 1 plus 3 equals 4. This means the probability of selecting index 0 is 1/4, which equals 0.25, and the probability of selecting index 1 is 3/4, or 0.75. When we call pickIndex repeatedly, we expect index 1 to be returned more frequently than index 0 because it has a higher weight. For instance, if we run the method 5 times, we might get a result like 1, 1, 1, 0, 1. This output reflects the expected probabilities, with index 1 appearing more often due to its higher weight of 3 compared to index 0's weight of 1. Now, in a more detailed example, suppose the weight array is w equals 10, 20, 30, 40. The total weight is the sum of all elements, which is 10 plus 20 plus 30 plus 40 equals 100. This means the probability of selecting index 0 is 10/100, or 0.1, index 1 is 20/100, or 0.2, index 2 is 30/100, or 0.3, and index 3 is 40/100, or 0.4. If we call pickIndex 10 times, we might get a sequence like 2, 3, 1, 3, 3, 2, 0, 3, 1, 2. Here, we see that index 3 appears most frequently because it has the highest weight, followed by index 2, and so on. These results are consistent with the probabilities derived from the weights. The method ensures that the frequency of each index being picked aligns with its relative weight in the array. The problem comes with several constraints and edge cases to consider. The weight array can have a length between 1 and 10,000, with each weight ranging from 1 to 100,000. Additionally, the pickIndex method may be called up to 10,000 times, so the solution must be efficient. Some edge cases include scenarios like a single-element array, such as w equals 10, where the only index, 0, should always be returned. Another case involves very large weights, like w equals 100,000, 100,000, 100,000, which the solution must handle without overflow or inefficiency. If all weights are equal, such as w equals 5, 5, 5, each index should have an equal probability of being picked. To achieve the desired functionality, the solution pre-processes the weights by building a prefix sum array. This allows us to efficiently sample indices by generating a random number in the range 1, sum, w, and using binary search to find the corresponding index. This approach ensures that the selection probabilities are proportional to the weights and that the solution is optimized for repeated calls to pickIndex. To understand how to approach this problem, let's first consider a brute force method. The idea is to create an expanded list where each index appears multiple times, proportional to its weight. For instance, if the weights are 2, 3, 5, the expanded list will be 0, 0, 1, 1, 1, 2, 2, 2, 2, 2. We can then pick a random index from this list, and because the frequency of each index corresponds to its weight, the probability of selecting each index is naturally proportional. However, this approach has significant drawbacks. Constructing the expanded list requires O(n) time, where n is the sum of all weights, and the space complexity is also O(n). For large weight sums, the memory usage becomes impractical, which limits its scalability. This makes the brute force method unsuitable for handling large datasets efficiently. A more efficient approach is to use prefix sums combined with binary search. Here, we first calculate a prefix sum array, where each element represents the cumulative weight up to that index. For example, with weights 2, 3, 5, the prefix sum becomes 2, 5, 10. Then, we generate a random number between 1 and the total weight, which in this case is 10. Using binary search, we locate the smallest prefix sum that is greater than or equal to this random number. The index corresponding to this prefix sum is our result. This method works because the prefix sum array effectively maps ranges of random numbers to specific indices, for example, 1 to 2 maps to index 0, 3 to 5 to index 1, and 6 to 10 to index 2. This ensures that the probability of selecting an index is proportional to its weight. The time complexity for initialization is O, n, to compute the prefix sum, and each query takes O, log n, due to binary search. The space complexity is O, n, making this approach far more efficient than the brute force method. Alternative techniques, such as reservoir sampling, are less relevant here since they don't directly address the need for proportional probabilities as effectively as this approach. Given the trade-offs, the chosen strategy is the prefix sum with binary search approach. It strikes an ideal balance between time and space efficiency. The prefix sum array is key to mapping random number ranges to indices, ensuring accurate probability distribution without the memory overhead of the brute force method. While the initialization step requires O, n, time, subsequent queries are highly efficient, taking only O, log n. This makes the approach well suited for large datasets and scenarios where multiple random picks are needed. The binary search ensures fast query times, which is critical in such cases. Additionally, this method directly satisfies the requirement of proportional probabilities without introducing unnecessary complexity. While the pre-processing step does involve some overhead, it is a one-time cost, and the assumption that weights are non-negative is reasonable for this problem. In conclusion, the prefix sum with binary search approach is the optimal solution for this problem due to its efficiency and scalability. It avoids the excessive memory usage of the brute force method while delivering a clean and maintainable implementation. The pre-processing step ensures that random index selection is proportional to the weights, and the use of binary search ensures that queries remain fast even for large datasets. This combination of efficiency, simplicity, and scalability makes it the best choice for solving the problem of random pick with weight. The problem we're solving here involves selecting an index from a list of weights, such that the probability of choosing a specific index is proportional to its weight. For instance, if the weights are 2, 3, 5, the total weight is 10. Index 0 should then be chosen with a probability of 2/10, index 1 with 3/10, and index 2 with 5/10. To achieve this, the brute force approach proposes creating an expanded list where each index appears multiple times, proportional to its weight. For example, index 0 would appear twice, index 1 3 times, and index 2 5 times. Once this expanded list is created, we can randomly select an index from it. The input to the function is an array of weights, and the output is a randomly selected index that satisfies this weighted probability condition. To implement this algorithm, the first step is pre-processing. We begin by computing the total weight, which is simply the sum of all elements in the weights array. This total weight represents the number of entries in the expanded list. Next, we create the expanded list itself, ensuring that each index appears a number of times equal to its weight. For example, given weights 2, 3, 5, the expanded list will look like 0, 0, 1, 1, 1, 2, 2, 2, 2, 2. Once the list is prepared, we move to random selection. Using a standard random number generator, we generate a random index within the range of the expanded list. Finally, we return the value found at that randomly chosen position. It's also important to handle edge cases, such as when the weights array is empty, when all weights are 0, or if there are negative weights. These cases should be treated as invalid inputs or handled explicitly. Expanding the list is a key step in this algorithm. It allows us to convert the problem of weighted random selection into a simpler problem of uniform random selection. By ensuring that each index appears in the expanded list in proportion to its weight, we achieve the desired probabilities when picking an index uniformly from this list. Random selection itself is straightforward, as it relies on standard random number generation. However, this approach has limitations in terms of space and time complexity. The space complexity is proportional to the total weight, meaning that as the weights or the size of the array grow, the expanded list can become impractically large. Similarly, the time complexity is dominated by the process of creating the expanded list, which takes n plus total_weight time. While random selection itself is very efficient at 1, the overall inefficiency of the list expansion makes this approach unsuitable for large inputs. The two main components of this brute force approach are the expanded list and the random number generator. The expanded list stores indices with repetition proportional to their weights, and the random number generator ensures uniform selection from this list. For example, given weights 2, 3, 5, the total weight is 10, and the expanded list becomes 0, 0, 1, 1, 1, 2, 2, 2, 2, 2. If a random index like 6 is generated, the value at expanded 6 is 2, which is the selected index. In edge cases, such as when all weights are 0, the total weight becomes 0, making selection impossible. This case must be handled explicitly to prevent errors. To improve this algorithm, we can avoid creating the expanded list entirely by using alternative methods, such as binary search on cumulative weights. This reduces space complexity to n, and time complexity to log n. Additionally, input validation can ensure weights are non-negative and non-zero, eliminating undefined behavior from the start. The problem random pick with weight involves selecting an index at random, but the probability of picking an index is proportional to its weight. The solution uses the prefix sum technique and binary search to achieve this efficiently. Explanation. Initialization, _init_. 1. The constructor takes a list W, representing the weights of the indices. 2. We calculate the prefix sums of the weights. For example, if the weights are 2, 3, 5, the prefix sums would be 2, 5, 10. This allows us to map each index into a range of cumulative probabilities. 3. The total sum of weights is stored in self.total_sum, which represents the maximum range for random number generation. Picking an index, pick index. 1. We use random.randint 1 self.total_sum to generate a random target value in the range 1 total_sum. This ensures that the range matches the cumulative weights. 2. To find the corresponding index for the random target, we perform a binary search over the prefix sums. The idea is to find the smallest index where the cumulative sum is greater than or equal to the target value. 3. The binary search ensures that the solution is efficient, with a time complexity of log n. Example walkthrough. 1. Suppose W equals 2, 3, 5. The prefix sums are 2, 5, 10, and total_sum equals 10. 2. If the random target is 6, the binary search will determine that it lies in the range 5, 10, corresponding to index 2. 3. If the random target is 3, the binary search will find it in the range 2, 5, corresponding to index 1. Efficiency. Initialization (n), where n is the size of the input list. Picking an index log n due to binary search. Total complexity efficient for large inputs, with pre-processing done in linear time and index selection in logarithmic time. This approach ensures correctness and scalability, making it suitable for competitive programming and real-world use cases. Here, we start by importing the necessary package, java.util, and defining the solution class. The main idea of this implementation is to use prefix sums to map the given weights into cumulative ranges, which will help us pick indices proportionally to their weights. We declare two private variables, an integer array called prefix sums to store these cumulative sums and an integer total sum to store the overall sum of weights. In the constructor, the input array W represents the weights. We initialize prefix sums to the same size as W and use a variable current sum to calculate and store the cumulative sum iteratively. For each weight in the array, we add it to current sum and store the updated sum into the corresponding position in prefix sums. By the end of the loop, total sum is set to the value of current sum, which represents the sum of all weights. This setup allows us to efficiently perform random selection later on. The pick index method is where the actual selection happens. First, we generate a random number within the range, 1, total sum, using math.random, which ensures that the probability of picking a number is proportional to its weight. This random number is stored in the variable target. Next, we perform a binary search over the prefix sums array to find the smallest index where the cumulative sum is greater than or equal to the target. We initialize 2 pointers, left and right, representing the bounds of our search. Inside the while loop, we calculate the midpoint mid and check whether the cumulative sum at mid is smaller than the target. If it is, we move the left pointer to mid plus 1, otherwise, we adjust right to mid. The loop ends when left equals right, and at this point, we return left, which is the desired index. This approach ensures an efficient and accurate selection process proportional to the weights. To solve this problem, we start by initializing the solution object with the given weights, in this case, 1, 3, 2. The first step is to compute the prefix sums. We initialize current_sum to 0, then iterate through the weights, adding each weight to current_sum and appending the result to the prefix_sums list. For the first weight, we add 1, so current_sum becomes 1 and prefix_sums is 1. For the second weight, we add 3, bringing current_sum to 4 and updating prefix_sums to 1, 4. Finally, we add the last weight, 2, resulting in a current_sum of 6 and prefix_sums of 1, 4, 6. This means the cumulative sums of the weights are 1, 4, 6. Additionally, we store the total sum of the weights, which is 6 in this example. Now we move to the process of picking an index based on the weights. When pick index is called, the first step is to generate a random target number between 1 and the total_sum, which in this case is 6. Suppose the random target is 5. To determine the index corresponding to this target, we perform a binary search on the prefix_sums array. Initially, left is set to 0 and right to 2, the bounds of the array. We calculate the midpoint as 0 plus 2, // 2, which gives mid equals 1. Checking prefix_sums, 1, we see that 4 is less than the target 5. This means the target must lie beyond index 1, so we update left to mid plus 1, which is 2. At this point, left equals right, so the binary search loop exits. The result is the index 2, which corresponds to the target 5 in the weighted distribution. In this example, we initialize the solution object with weights 5, 1. The first step is again to compute the prefix sums. Starting with current_sum is 0, we add each weight in turn. Adding 5 results in a current_sum of 5 and a prefix_sums of 5. Adding the second weight, 1, brings current_sum to 6 and updates prefix_sums to 5, 6. This means the cumulative sums are 5, 6, and the total sum of the weights is 6. These values will guide the random selection process. For the pick index method, we generate a random target between 1 and the total sum, which is 6. Suppose the target is 2. To find the corresponding index, we perform a binary search on the prefix_sums array. Initially, left is 0 and right is 1. We calculate mid as 0 plus 1, // 2, which gives mid equals 0. Checking prefix_sums, 0, we see that 5 is greater than or equal to the target 2. This indicates that the target lies in the range covered by index 0, so we update right to mid, which is 0. At this point, left equals right, so the binary search terminates. The result is index 0, corresponding to the target 2 based on the weights. Here, we use weights 10, 20, 30, and initialize the solution object. The prefix sums are calculated by adding each weight to a running total. Adding 10 results in current_sum equals 10 and prefix_sums equals 10. Adding 20 brings current_sum to 30 and updates prefix_sums to 10, 30. Finally, adding 30 results in a current_sum of 60 and a prefix_sums of 10, 30, 60. The cumulative sums of the weights are 10, 30, 60, and the total sum is 60. These values enable efficient weighted random selection. To pick an index, we generate a random target between 1 and the total sum, which is 60. Suppose the target is 25. Using binary search on the prefix underscore sums array, we start with left equals 0 and right equals 2. Calculating mid as 0 plus 2, // 2, we get mid equals 1. Checking prefix underscore sums, 1, we see that 30 is greater than or equal to the target 25. This suggests that the target lies in the range of indices 0 to 1, so we update right to mid, which is 1. With the updated range, we calculate a new mid as 0 plus 1, // 2, giving mid equals 0. Checking prefix underscore sums, 0, we find that 10 is less than the target 25. Therefore, the target must lie beyond index 0, so we update left to mid plus 1, which is 1. Now left equals right, exiting the loop. The result is index 1. This process highlights how prefix sums in binary search efficiently map the random target to the correct weighted index. The time complexity of this problem can be broken down into two main components, initialization and the pick index method. First, during initialization, we calculate the prefix sum of the input weight array W. This involves iterating through the array of size n once, and since each operation, like adding the current weight to a running sum and appending it to the prefix sums array, is constant time, the overall time complexity here is O, n. Now, for the pick index method, we perform two key operations. Generating a random number between 1 and the total weight takes constant time, so O, 1. However, finding the index corresponding to this random number requires binary search on the prefix sums array. Since binary search operates on an array of size n and has a logarithmic growth rate, this step takes O, log n. Combining these steps, the overall time complexity for a single call to pick index becomes O, log n. Looking at the overall time complexity, let's consider the scenario where pick index is called k times. The initialization step remains O, n, as it is only performed once. Each pick index call takes O, log n, so for k calls, the total becomes O, k * log n. Adding these together, the final overall time complexity is O, n plus k * log n. Now, for space complexity during initialization, the prefix underscore sums array stores the cumulative weights. Since this array is the same size as the input array W, its space requirement is O, n. Additionally, we use a single scalar variable, total underscore sum, to store the sum of all weights, which takes O, 1, space. Summing these contributions, the space complexity of initialization is O, n. Turning to the space complexity of the pick index method, we see that it uses only a few scalar variables, target, left, right, and mid. These are used during the binary search and require constant space, or O1, since no additional data structures are allocated. Consequently, the space complexity of pick index is O1. When combining both initialization and pick index, the overall space complexity is dominated by the prefix underscore sums array, which requires O, n, space. Therefore, the total space complexity for the optimized approach is O, n. To understand the efficiency of the optimized approach, let's compare it to a brute force method. The naive approach involves generating a random number and iterating through the weights array to find the corresponding index. Each call to pick index in this method takes O, n, time. For k calls, the total time complexity becomes O, k * n. In terms of space, since no additional data structures are used, the space complexity remains O1. Now, the optimized approach significantly reduces the time complexity of pick index to O, log n, using the prefix sum array in binary search. However, this improvement comes with a trade-off. The space complexity increases from O1 to O(n) because of the additional storage for the prefix sums. The mathematical reasoning behind the efficiency of the optimized approach lies in the behavior of binary search. During binary search in the pick index method, the range of the search is halved at each step. For an array of size n, this process completes in a maximum of log base 2 of n iterations, leading to a time complexity of O log n. Summarizing the overall analysis, the one-time initialization cost of O, n, is the dominant factor in setup, while pick index achieves efficient index selection in O, log n, per call. For a large number of calls, the optimized approach drastically reduces the total runtime compared to the brute force method, making it highly efficient for scenarios with high query frequency. When working on this problem, there are several common mistakes to watch out for. First, it's essential to correctly interpret the problem requirements. For instance, you need to determine whether the weights represent probabilities, cumulative sums, or absolute counts. Misunderstanding this can lead to solutions that fail test cases or exhibit incorrect behavior. Another frequent issue is overcomplicating the solution. Some might try using advanced data structures like binary search trees when a simple array or prefix sum would suffice. This over-engineering not only increases implementation time but also makes debugging more challenging. Additionally, floating point precision errors can sneak in when normalizing weights. For example, if weights are very small or very large, rounding errors can accumulate, causing biased sampling. Finally, an inefficient brute force approach, such as creating an expanded list proportional to the sum of weights, may seem intuitive but becomes impractical for large inputs due to high memory and time usage. Avoiding these pitfalls is key to an efficient and correct solution. Now, another common issue arises with off-by-one errors when working with prefix sums for weighted random selection. It's easy to mishandle inclusive or exclusive bounds, which can skew the sampling probabilities. This might result in some indices being oversampled while others are undersampled. Beyond these mistakes, it's helpful to understand the broader context of this problem. Weighted random sampling is a common technique in fields like machine learning, simulations, and gaming. Mastery of tools like prefix sums and binary search will serve you well, as they often appear in variations of this problem. For optimization, focus on pre-processing the data. For example, constructing a prefix sum array as O, n, while querying with binary search brings sampling time down to O, log n, making it far more efficient than brute force approaches. During interviews, always discuss trade-offs, such as pre-processing time versus query performance, and demonstrate your ability to balance these factors. Also, be ready to handle edge cases, like scenarios with zero weights, extremely large or small weights, or invalid inputs such as negative weights. This problem is part of a family of related challenges that test your ability to implement weighted random sampling in different contexts. For example, problem 497 involves random point selection in non-overlapping rectangles, which uses a similar weighted area approach. Problem 478 asks you to generate random points inside a circle, requiring geometry-based sampling techniques. And problem 382 explores random selection in a linked list using reservoir sampling. These variations broaden your understanding of sampling techniques. Regarding alternative approaches, brute force is the simplest to implement. It involves expanding weights into a list and sampling randomly. However, it's inefficient for large inputs due to high memory and time costs. A better approach is to use a prefix sum combined with binary search. By pre-computing the cumulative weights, you can achieve efficient querying, though there's an upfront O, n, pre-processing cost. Rejection sampling is another option, where you repeatedly sample based on probabilities until you get a valid result. It's pre-processing free but has variable runtime. For high query volumes, the alias method is worth considering. It pre-processes weights into two arrays for constant time sampling, though the setup is more complex. Each approach has its trade-offs, and your choice should align with the problem's constraints and requirements. Great job! To summarize, we tackled problem number 528 by focusing on weighted random selection using a brute force approach. We explored the trade-offs in complexity and discussed its applications. Thanks for watching. Be sure to stay tuned for more coding challenges and solutions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!